Good morning. This week in lab, we are looking at oscillations. So in class, we've been looking at oscillatory motion. This is kind of our last set of topics in the mechanics part of physics. So let's take a look and see what it's going to be like. What we're going to do is we're going to take a spring. So the springs look like this. And we're going to attach this to some kind of a support. And then what we'll do is we will attach different weights. So, I can attach 100 grams and watch the oscillations that are set up. And then I'll attach a couple 100 grams, 200 grams, and then look at the oscillations, 300, 400. What we're going to do is we're going to go all the way in 100 gram increments, and we'll just keep increasing the mass. Now, what we've learned in class is that as you increase the mass in an oscillating system, the oscillations slow down. That means the frequencies drop off and the periods get longer. So we'll be measuring the periods. Now we did this, what lab was it? The pendulum gravity lab. Maybe that was a lab that we did where the pendulum was swinging back and forth and we would time the different cycles. So this is kind of similar. What we're going to have are cycles where this is oscillating back and forth. And as the mass increases, we'll look and see what's happening with the period. Now, in addition to using an oscillatory set of measurements to find out a value of K, that's what we're headed towards, we can also use equilibrium. That's even easier. We've been looking at springs since chapter 7, I think, and we've been using springs to represent the elastic properties of materials or different mechanical systems that have elastic properties built into them. And so for the equilibrium method, what we could do is here's some kind of a support, here is the spring attached, and then here is some mass. And what we could do is find where the equilibrium is. Now, in order to get a K value, we need to do some measurements of X, where X is telling us how much did the spring stretch out. So I've got to do a measurement of where the spring is with nothing attached. So we would start off with nothing at all attached, measure that location, and then add 100 grams and measure the new location of where the spring is. So every time I add 100 grams, I got to go back in for this equilibrium method. I have to go back in and measure the distance. Now, all of the X values will come from taking that original measurement of, where was the spring when nothing was attached, measure that location. And then let's say we add 100 grams and it stretches to here. Well, I've got to be able to use numbers or take the measured values and determine what the X values are. So you have to pay attention a bit to the X values. So, I'm going to be collecting data. We'll take a look at the setup here in just a minute. And, but I'm going to have a bunch of values written down, and from those, we have to decide how do we go back in and determine the X values. So for this, we'll have, a data table with, masses, again, 100 gram increments between 0 all the way up to 1,000 grams. And at 1,000 grams, the spring is stretched out quite a bit. You'll get to see that when we look at the setup here. And then I got to get X values for all of those. Now that seems like something we could graph. It's been a while since we graphed anything, maybe? Anyway, I think we need to do a graph on this. And the graph for this would be putting the distance that the spring is stretched as a function of m. Now, at equilibrium, Kx equals mg. The force from the spring upward matches the force of gravity downwards acting on the object. And that says that the X value is mg divided by k. Now, one way we could write that equation is to say X is equal to g divided by k times m. And that formula, the form of that, suggests that we could collect a bunch of data where m gets larger and larger and larger, and then we could measure or write down all of those X values, and we could graph it. So what we're going to do is we're going to graph X versus M. And again, what this formula suggests is, first of all, it should be a linear relationship between x and m, and it looks like it should go through the origin. So we're looking for a function, we're looking for a linear fit. Here is all the data on my graph, all the data points. Remember, the data points always get shown as data points. And then any kind of a fit, then we'll add that line in. So I can do a linear fit, I can constrain the fit so that it goes through the origin, and then looking at the formula here, it says that the slope of my line will be given by g over k. So this is vertical variable equals slope times horizontal axis variable. That's how the straight line fits should work. So I can get a value of k by looking at the slope. So I'm not getting values of k, well, I guess I could from individual measurements also. So we could get values of k individually. We could add a k column here if we wanted to. That's actually not a bad idea. Maybe I'll add that in. Yeah, maybe I'll add that in. Okay, so we can get a series of individual k values from here, but what we're really after is the averaging. So what we want to do is average all of this. If this is an ideal spring, then x should be proportional to m, and what we'll see is the data will line up. Now, again, that's the equilibrium method, and I think that's actually written up as the kind of a check once we have done the oscillation method. So we're really mostly interested in the oscillation method for the day. This is kind of the new item that we want to look at. Now for oscillations, for simple harmonic motion type oscillations, we say that the frequency, the radiance frequency squared, is equal to the force constant divided by the mass. Now notice, in the oscillation case, I am including what I'm calling an effective mass of the spring. And by effective mass, this is what we mean. At equilibrium, the mass of the spring doesn't really come into play. So the mass of the spring itself, when I stretch this spring out, the mass of the spring itself doesn't make any difference. But if I'm oscillating, if the spring is oscillating back and forth, the spring itself will have inertia. The spring's mass will create an inertial effect. Now, I'm trying to think back of all the examples we've looked at in lecture and all the homework problems. I think they've always assumed that the spring has no mass. But you know what? Springs have mass. So what we can do in today's lab, in addition to measuring K, is we can come in and figure out how much of the spring's mass is going to show up in the formulas. Now, at first you might think, well, let's just put the whole mass in, right? But the whole spring isn't oscillating back and forth with the same amplitude. The object at the bottom is oscillating back and forth. The entire object that we have attached is going to be oscillating back and forth. But different parts of the spring oscillate with different amplitudes of oscillation. And so there's a theoretical set of calculations. We're not going to derive that. But there's a theory that suggests that the effective mass of the spring is 1/3 of the total mass of the spring. So we can get a mass measurement. I can set this on a scale and read this off. Looks like 161.7 grams. So we can get the actual mass of the spring. We can write that down in some data. And then we can do a comparison. So what we'll do is, let's check and see if the effective mass of the spring really is given by roughly 1/3. Now where that theoretical approach comes from, it comes from energy conservation. It says that when we set an ideal spring, I guess it's an ideal spring with mass. We've had different categories of ideal springs. And up till now, I think the ideal springs we've assumed don't have any mass at all. But this time we're going to keep all of the previous idealizations that the springs don't heat up, they don't generate any thermal energy, they will oscillate back and forth forever. We're going to keep those features, but we're going to allow the spring to have some mass. So when we do that, what we can do is we can actually use energy conservation and say as this thing oscillates back and forth, there's a kinetic energy associated with motion of the spring itself. And so, I mean, you can take a shot at the derivation if you want to. What you do is you just conserve mechanical energy within the object at the bottom and the spring, and you end up with this factor of 1/3 as to how to take into account the kinetic energy of the spring. It comes down to integrating over the kinetic energy of the spring as it oscillates back and forth. Okay, I'll say that much. If anybody's interested in seeing this, stop by office hours and we can take a look at the derivation. So now, how does that effective mass show up in our measurements anyway? Well, we're going to put it into the formula right there and say that the oscillations will actually be slowed down by the presence of the spring's mass. And right now we're not suggesting how much that's going to be, but we'll just put it into the formula. Now, instead of, when we're doing the actual measurements, we're going to be measuring the period, not the radiance frequency. So we want to get the radiance frequency converted into 4 pi squared over period squared, and then I can take this formula and that formula, and I can set them equal to each other and solve. I'm going to solve for period squared. Period squared is going to be equal to 4 pi squared over the spring constant, over the force constant, times the mass of the object. Now remember, that's this object right here, plus the effective mass of the spring. So we're combining both of these masses together. And again, what we're going to do is a graph. I mean, this just really suggests, let's take a bunch of measurements at a bunch of different weights, a bunch of different masses. We'll start at 100 grams, and then 200, 300. We'll work our way up to 1,000 grams. So at first, the spring is stretched out a little bit, and then it stretches out more, and then it stretches out more. In any case, we can measure the period of the oscillations. Now, the period of the oscillations, if I just measure one, it might have some real uncertainty to it. So we're going to measure, I think 10 cycles should work pretty well. I've been playing around with the setup, and the cycles themselves are like a few seconds. And if we do 10 of those, if we measure something like 20 seconds and then divide through by 10, that will help with the precision of our measurements, I think. So let's do that. Let's plan on 10 cycles, how much time, and then we just take that number and divide by 10, and that's going to give us the period. Now, the formula itself is not in terms of the period, it's in terms of period squared. So I added one more column in the data table. I got to take each one of the individual periods and square it, because what we're going to be putting on the graph is this. I'm going to be taking data from the t squared and data from the m columns and plotting that onto this graph. What this formula suggests is that the slope of the data should be given by 4 pi squared over k. So here's my graph. Here is the data with those nice prominent data points. Let people know where your data actually is, and then a linear fit. Now this time, the linear fit is not going to go through the origin, and that's because this is our variable. The variable is little m, but m prime is not a variable. M prime is some fixed number, and so this is going to become the x-intercept. If you take a look at a formula for a straight line, this is the y-axis, this is the vertical axis here, n is along the x-axis, and that says that this is something that shifts the graph, and it shifts it in the negative direction by an amount m prime. So we're going to get m prime by determining the x-intercept. Now, you can do these graphs by hand, or you can do them using computer generation. If you use something like Excel for these graphs, what you can do is you can have it give you a function, right? And tell you what the slope is, and then you can get the k value by taking 4 pi squared over the slope. Okay, watch units. Make sure that you're keeping all the units straight. I'm guessing I mean, by the time you do this formula here, you want everything in just standard units. Everything in kilograms, everything in, well, you can do this calculation and then adjust everything back into standard units. Now, the m prime is going to come from the x-intercept. This is the data table here. We talked about the theoretical prediction for the effective mass. So once we get the k value from the equilibrium method, and we get the k value from the oscillation, simple harmonic oscillation method, we can compare those. So let's write down what the equilibrium number is, and then write down what the oscillation number is. We could do maybe a % difference. Now, I can tell you this too, we could also do a % difference with accepted. So you guys can decide how you want to format your results table. But originally, when when these springs were first purchased, they were supposedly had K values of 10 newtons per meter. Now, we've had these for a number of years. When I look at the springs themselves, this one looks okay. Some of them are stretched out. I picked one that looked like it was still pretty healthy. I don't know if the K value has dropped off from that 10 newtons per meter, or this particular spring. But we will find out. So do some comparisons here. See what you get for the equilibrium method. See what you get for the oscillation method. Maybe do some comparisons with the accepted values. Put together some results table. Whatever you feel like would be most effective in kind of presenting the results that you have come up with. So did we get everything covered here? I am hoping we did. We talked about all the formulas. We talked about how the effective mass comes into play and how we're going to determine that from the graph. So I think we're looking pretty good. So if you guys have questions, stop by and we'll get those looked at. But I think right now we want to move on. Take a look at the setup and we'll see what taking these measurements is going to look like. Here's what the setup looks like for our simple harmonic motion lab, for the oscillation lab. Let's take a look at this. So I got a couple of posts and I anchored those into the countertops pretty securely. And then I put a bar across the top, and here is our spring that we're going to be looking at. A little bit of wobble, but we'll see if that has an effect once we start doing the runs. And then I've got, currently I have like 100 grams on there attached to the spring. I've got the hanger itself is 50 grams, and then there's a 50 gram mass on that also. And then what I've got ready here is I've got a stack of 100 and 200 gram masses. I've got some tape that I use to anchor everything in place. I've got the timer ready to go here, my scissors, and some paper ready to start taking notes. So I'm going to set this camera up and see if we can put it into a position and check to see if we can see everything. Everything looks pretty good right there. Well, let's take a look and see what taking some of the measurements might look like. So the first part of the lab talks about looking at oscillations. That's really kind of the feature of this lab. That's what we're trying to look at. And so it's only 100 grams right now. I think I'm going to put another 100 grams on or so. And I'll do a 200 gram measurement and demonstrate that for you guys. So what I'm doing is, first of all, I'm looking at the equilibrium point, just kind of judging where that is. Now, one of the ideas of the lab is to do a series of measurements with relatively small amplitude, even smaller than this. I could do something, I think I suggested like 1 centimeter of amplitude. So something like that maybe. And then something larger, something like 5 or 10. And so we could do a set of timing for the larger amplitude and the smaller amplitude. And the prediction is, if this is an ideal spring, that the periods of the oscillation should be the same. So we'll see if that really works. Now, the spring itself is not massless, and so we're aware that the spring itself will have an effect, the mass of the spring will have an effect on the period of oscillation. And it's entirely possible that with low masses, 100, 200 grams, that the spring's effect, it could show up. We'll have to see if it shows up in the data. Once we get up to higher masses, I'm guessing that the spring's mass will have a smaller and smaller effect. But again, we'll have to take a look and see what the data looks like. So we've got the spring set up here. I got my timer ready. And what I can do, first of all, I don't have to synchronize the timer with the release of the spring. What I can do is get the spring oscillating. That looks pretty good, That looks like a centimeter amplitude. And notice it's not damping out very fast. So this is going to oscillate for a good long time. And so I can grab my timer, and I just want to count reliably 10 cycles. And so when I think at the bottom, I'm going to hit start and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I stopped right on that 10, and I got 11.11 seconds. So this is with 200 grams. I guess I should be writing these numbers down. So that's with the 200 grams. Now, what would happen if we increase the amplitude? So here we go. Ooh, I think I overdid it. So I'm going to reset my timer, and again, I'm going to count 10 of these cycles and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this came in at 11.00. What were the chances? So 11.00 with the large amplitude, and 11.15, was that it, for the smaller amplitude. So pretty close, right? And now that was for 10 cycles. So I'm going to have to divide through by 10. So at the lower amplitude, that would be 1.15 seconds. And at the larger amplitude, 1.10. So a difference of 5/100ths of a second. Now that sounds pretty similar to me. It sounds like there's no significant variation in the timing. I know that my response time could possibly be that large. I could, my response time could be off by a few tenths of a second. And that's kind of the difference that we saw. So anyway, we'll do a whole series of those measurements. Let's try one more, I guess. So I'm going to put on, I'll put on more. 300, 400. Ooh, let's try something really large. 500, 600, 700. Can you guys still see this? Maybe not. Maybe it's gone too low. Let me check real fast here. It's not worth watching if you can't see it. And I have to say, with my viewfinder, I can't really tell. Oh yeah, it's definitely below where you guys can see. So let me, I'm going to angle this up a bit. There we go. All right. And here we go. I'm going to do that timing again, same thing I was doing before. And so I'll do a small amplitude. I could make it smaller than that. Okay, reset, and at the bottom, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, and I got to be ready. 10. 20.06 seconds. 20.06. Let's give it a larger amplitude now. So here is the larger amplitude. I will reset and start. 1, 2, 3, 4, 5. I think something's going to fall off. 6. Okay, that didn't work so well. Now what you're seeing is, I noticed this when I was doing some preliminary runs. When I went to these higher masses, I started to see the spring twists. So as it stretches out, it also rotates a bit. And I found that when I looked at the larger amplitude oscillations, they were quite different. So as I went to higher and higher masses, I got more and more of that torsional effect. And along with that, I saw that the times didn't match anymore. So it could be that we will, and I'll write something up in the data sheet, but it could well be that at these larger masses, we won't, well, let me try this one more time and we'll see. We may not be including, I'm going to take the data, but it may be that we won't be, let me do this quickly. So, start. 1, 2, now it's not as large as it was before. 3, 4, 5, 6, 7, 8, 9, 10, 20.56. So there's a small amount of torsional effect here, but it does seem like when we get to these larger masses, there's more of a torsional effect, and the timing between small and large amplitudes don't match up as well. So, and I'll make some note of that in the in the data notes. But that's basically it. That's what these measurements look like. Now, one of the crazy things that happened is for years, when we were doing this lab, it seemed like there were like 2 different results that the different lab groups would end up with. And I was always curious. There was one lab group where all the data seemed to line up more consistently, and then there was a second group where the data didn't quite line up as well, and and the numbers didn't quite match between the equilibrium method and the oscillation method. And so I went back finally, after many semesters, I went to one of these groups that had come up to me and shown me the results, and I said, you know, let me come back and watch you guys do this. And I found out the source of error in a lab, which was unexpected, is counting to 10. So what I found was this. What students were doing in these groups, and it had gone on for many semesters, is they would, with the timers, when they started the timers, they would go 1 when they started the timer. And that meant they were only counting 9 cycles instead of 10 cycles. So, mystery solved. So it turns out that when you get that first starting time, you have to say 0, 1. You don't say 1 until you've got 1 complete oscillation completed. All right, so that's what the oscillation part looks like. Let me reset this a little higher now. Let's go back up and look at the equilibrium measurements. So with the equilibrium measurements, what we want to do is go back, and again, we want to add 100 grams at a time onto the, let me take a bunch of this stuff off. So for the equilibrium method, what we want to do is get a 2-meter stick set up. Here's my 2-meter stick. Now, for whatever reason, I measured from the floor up. I don't know if that was a good idea or not. Maybe not. But, so here I am measuring from the floor. I know what I want to come up with is something where I can consistently measure the height. And so what I've got right here is, this is like at 166.4 centimeters. And what I'm measuring to is this lowest rung on the spring. So that would be a measurement with the spring in place here. And then what I can do is I can add 100 grams on. And then adjust this so that it's at equilibrium. I damp out any oscillations. And then I remeasure that same reference. And so again, the reference I'm going to use is this lowest part of the ring. And for this measurement right now, it's looking like 155.2 or something. And then I just continued. So I got a series of numbers. Now, those aren't the final numbers yet. What I'm going to have to do is take differences. Initially, we're going to say the spring was not stretched out at all, although due to its own mass, it actually was stretched out a bit. But we're going to start with that 0 measurement, and then as we add 100 grams on each time, we'll get the 2 meter stick out, and we'll get a new measurement. Again, the reference that we're going to be working from is the lower rung of that spring, and I'm now at like 143 point something. I'll go back and do these more carefully and come up with a data sheet. So that's what I want to do. And then we'll put another 100 grams on. So if what we've been talking about in class really works, what we would expect is that this spring, it might not be completely ideal, but it's going to show some of the properties of an ideal spring. And so what we can do then is we can make differences. We can take the differences between each of these measurements. Okay, and you can see every time we add 100, this thing is going to drop to a new equilibrium point. I'm going to get all those recorded, and we can see. So the K values that we come up with from the equilibrium method, that can be compared with the K values coming up from the oscillation method, and we'll see how they compare. See if all of these formulas we've been deriving in class, see if they work in reality. So I think that's it. So I think we've looked at everything we need to look at for today. Again, if you guys have any questions, stop by. But that is that's the oscillation lab.